Hello, welcome. So now we're going to be looking at 5.2, which is, we've talked about the Graph ADT and how we can conceptually wrap this into some kind of .h file, but now we have to talk about how to implement it. And unlike trees, there's actually a few different ways to implement a graph, which is kind of what makes this topic a bit more interesting. And they all have pros and cons. Like, how did we implement binary trees? We implemented it as a linked list with children. And that kind of makes sense. It's very hard to do binary search trees. They do work, refresh the page. It's very hard to do them with like array structures, essentially. So it's going to be another linked structure like a tree, except there's a few different ways. There are also an array structure. We're going to look. Oh my god. I really screwed up this bit this week, I guess. So just a bit of context. So the problem is that when I write these slides, when I make these slides, I always start off here being like, why are we doing this? And I always think about that when we do the lecture. And then I'm always like, I'll fill this in at the end once I've like mapped out the slides. And I just forgot. I'm sorry. So why do we care about this? This slide is just a dump. I'm sorry. Just ignore that one. There's no excuse for that. That's just me forgetting things. So before we look at different graph implementations, right? We know this from all the lectures we've done in weeks 3 and 4 in particular, where you have this implementation and that implementation, AVL trees and 2, 3, 4 trees, and they all have different kinds of properties. They all have different benefits and drawbacks, right? Like an AVL tree has a higher storage cost, but it can be quicker at generally maintaining tree balances. So graph implementations are totally the same, where some of them have drawbacks, some of them have benefits, and which one is better or not really depends on the application you're using. And a really important property of graphs that actually helps, like one of them that actually helps us make sense of the best decision, is that if we have a graph, and we're going to define V and E as the number of vertices and number of edges. If we have a graph with V vertices, so maybe 10 vertices or 20 vertices, the most number of edges that graph can have is V minus 1 on 2. Now, you know, that kind of looks very arithmetic summy, but you could go and try and derive that yourself if you want. Like, go make yourself like a complete graph, like here, 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 and here, and think about all the general behavior. Like as you draw this out, right? Like the first one has 3 edges, and the next one has 2, and the next one has 1. You know, so it is essentially an arithmetic series. So you could sum all that up, and you know, that's how many edges you'd in theory have. One thing we like to say is that if the number of edges is close to V squared, so if there's V vertices and there's V squared edges, then we call the graph dense. You can't actually have V squared edges, but if it's getting closer to V squared, we call the graph dense. A complete graph, where all the edges are connected, is the definition of the densest graph possible. And then you have graphs where the number of edges might be closer to V, which is basically a linked list, right? Because if you've got 10 nodes and you've got 10 edges, then it's kind of linked list-ish. Then we call the graph sparse. So again, you have this kind of graph over here, which is dense, and then you might have a graph over here, which is what you would call sparse. There's not many edges per vertex. You could even have graphs like this where there's no edges per vertex, which is super sparse. And that's the edge to vertex ratio. And that's really important because some graph implementations are extremely applicable to dense graphs, and other graph implementations are a lot more applicable to other implementations. That's what we're going to talk about. So what is a graph implementation or a graph representation? So I mean, a representation, the word just means like how would you model it. Implementation is a bit more like how would you code it, so somewhat interchangeable. If you had a graph like A here, you probably already have an intuitive sense that B is the same graph. Now, you look at it, you might think, oh, that looks like a different... Oh, wait, it's the same graph. But They're the same graph. They got the same nodes, the same edges. They're just drawn differently. It's just a different representation of the same thing. And we could expand that and say, actually, this over here, C, is actually also a graph. It's a series of node and edge pairs. Because this graph is just 1 and 2 are connected, 2 and 4 are connected, 3 and 4 are connected, 4 and 5 are connected, 1 and 3 are connected, and 1 and 4 are connected. So that's all here. And then in this one, same thing. Like, these are just different arrangements of the same thing. So there are lots of different ways we can represent graphs. And there are 3 primary ways that we would actually do it in code. And the first one is an array of edges. An array of edges actually is quite similar to what you see here, where it's just like a whole bunch of edge pairs like this. It's just like, these are all the edges that exist and the vertexes on either side. So you have an array of edges. We have an adjacency matrix, which is essentially storing all of the information about nodes and edges in a giant 2D array, or like a giant matrix. And then we have an adjacency list, which is a bit more, I think it's somewhere in between, you'd say, where for each node, we essentially store each node or vertex in the graph, and then we store all the edges that are associated with it. We're going to talk about all 3 of these. So first one is our array of edges. So we'll go through these in order. And these graphs are where the actual storage of the graph is literally just an array with edge pairs. Now, like, what's an edge pair? It's just the 2 vertices. It's like a pair or a tuple. You could imagine these as like the structs we saw back in 5.1, where it was just like a struct with like vertex and vertex. So this kind of graph here, you would just represent like this. You know, there's 4 edges in this graph, so our array is going to consist of 4 edges like that. And then this graph over here is a similar thing. This one's directed though. So, you know, for director graphs, the ordering, oops, what is that I just dragged? Try to drag this. Yeah, so for directed graphs, the ordering of vertices within an edge pair denotes direction. Great. So what are the what are the kind of key things about array of edge structures? Well, firstly, it's very space efficient because it only stores information about the edges that exist. So it kind of just grows linearly with the number of edges. So it's an extremely space efficient storage method. It's not super perfect because, you know, and you can see in this graph here, we're actually storing 1 3 times here. Now, of course, 1 could be a pointer, which would make that in some circumstances lighter in storage usage, but there's a little bit of redundant information here. There are probably more efficient ways that this graph could be represented, though. Hey, point 2. This one is not my fault. I copied this from another slide, so that's funny. Yeah, so it's pretty space efficient. Lookup is a little bit complex because if you want to check if an edge is in a graph, you have to kind of go through all the array items like a normal array search. And yeah, you could sort the array, but then there's even more overhead in constantly sorting the array, right? Because we learned this with trees. We don't like to have to constantly be resorting arrays. Obviously, you could get around that by, you know, you could probably store an array of edges in a binary tree or something crazy if you want. But like the general approach here is that you're storing some kind of list of, you know, vertex pairs which represent edges. And adding and deleting and lookup are pretty, you know, complex. When we say mildly complex, we're basically saying it's array-like in nature. So adding and deleting from an array is relatively complex. Looking up in an array that isn't sorted is relatively complex. Looking up in a sorted array is pretty easy, but sorting it can be relatively complex. In these undirected graphs, which are the ones we're looking at this week, the ordering of these pairs doesn't matter, no. Directed graphs it might, or it can, though we're not talking about that at the moment. In terms of the array of edges implementation, we have a graph representation, and if I just pull up what we had in VLab before, this is, so if you think for a second here, this is our ADT. So if we were to then start making a you know, graph representation and actually complete this incomplete type here, this struct graph rep, this is what it might look like here. So let's think about what this is. So the actual struct stores a few things. Firstly, it stores the number of vertices in the graph and the number of edges. That's pretty much true in all graph implementations. They all store some semblance of the number of vertices and the number of edges. Then we have the size of the edge array, because any kind of array we store, we need to, maintain the size of it. That's kind of true for a lot of data structures. And then the last thing we have is a pointer to an edge, which is actually going to be an array of edges, because we're going to have to malloc this when we create it. So edges here is just a pointer to an edge array. Because it's dynamically sized, we will need to malloc it, right? And free it. So think back to like lab 3, I think it was, with the dynamically sized array where like you had to realloc the queue. Sorry, I think it was. It's the same kind of thing here. We can't statically define this. Of course, we could just say edges like 50, but then you're capping the size of the graph, which we don't really want to do. So that's kind of why we have this pointer-like structure. And in reality, what that ends up being is that for a graph like this on the left here, this undirected graph, you have these nodes and these vertices. The representation here has 4 nodes and 4 edges. So that's why NV and NE is 4. And then you have N, which is the number of edges and size of the edge array, which is the actual size of the overall array here, not the size of the number of edges. Like when we say edge array, we literally mean the edge array itself, the whole array, even if it's not filled yet. And that's how we keep track of the size of the physical array in memory. Edges is a pointer to that array. So this all here is stack memory, and over here, this is the stuff that we've malloced. So this thing would be malloced whenever we create a new graph or potentially have to resize it. And that's just the general structure we have. The pseudocode for this is relatively also straightforward. It's like when you create a new graph, you're essentially populating the struct and mallocing enough memory for the edge array. When you insert into the graph, you're pretty much just going to the end of the edge array and putting something in there. So inserting is pretty trivial. You just go loop, 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 put it at the end. I'm just looking at this again. The reason we have to loop through the array is to avoid duplicates. So with an array insert, typically you don't need to do any iteration, any traversal, but because we want to avoid duplicates, we do actually have to go and check all of the elements first. So we check all the elements to see if it's there, and yeah, if it hasn't been found, then we just insert it into the array and increase the number of edges by 1. And naturally, you'd have to check that the array is big enough to deal with it. And a similar thing with remove edge. Though you can see this really trivial pseudocode here is, again, basically looking through it, trying to find it. And if it finds it, it'll get rid of it. Though I don't think there's any reshifting that happens here, because again, the problem with array structures is that you need to, like, you don't have to, but like if you want to make best use of the storage after you delete something, you often have to slide everything back. And then showing edges is pretty straightforward. Like typically when we do a graph print, see, trees are hard to print. You can do it recursively. We've talked about that. But graphs are even harder to print because there's no real way we could structure them. So the usual way that we print graphs is just by a series of edges. So we just print out the series of edges. And that makes this quite trivial here. I changed some of the pseudocode from some of the notes. Like I mainly cut things out of old pseudocode, but some things like this are left in. I'm pretty certain this just means and. I don't think it's anything more complicated than that. I could change it to a double ampersand, yes, and in some slides I have, but sometimes I don't like change everything because I'm rewriting a lot of pseudocode sometimes. Like sometimes you'll see me, I'll change this to a not equals to and a few other things. Yeah. So that's like all the basic operations. Diorora says, do we just allocate v times v minus 1 on 2 as in the total number of possible edges spaces for the edge array? Totally depends on your, like, it totally depends on the circumstances. Like if you know you're dealing with complete graphs, then probably one malloc's going to be a bit cheaper. if you know you're dealing with a more sparse array, then probably not. You'd probably just malloc something smaller, like V, or you could have a dynamic one where it you know, it reallocates itself as it gets bigger. And yeah, look, so I know these things might be confusing to some, but one of the other reasons that I don't get too caught up about the pseudocode thing is because there's no standard for pseudocode in terms of there's no like if you go to like Wikipedia and you're like breadth first search, which is a topic we talk about tomorrow on Thursday, again you'll see a lot of things like this. I mean, this is an actual implementation in a you know, C like language. That wasn't quite what I was looking for, but you know, lots of pseudocode is very different, and there's a certain degree of just kind of getting used to looking at. I'm probably not going to find it. Things like this, and it's like, sure, you know, the up arrow might be a bit confusing to some here, but it's important to try and look at something and imagine in context. And this is not something you're used to seeing, right? This little arrow, like, what the hell does that even mean? That's basically a weird way to write an equal sign. So there is no standard for it. And I think that's a really important thing to clarify. It's also why we don't teach you, like, this is the particular way to write pseudocode. RStudio. So that's the pseudocode for this. Now, the full implementation of the array of edges is actually sitting inside of our class folders. So you can find this on WebCMS3. If you go to code here, you'll actually see all of this code. I'm just going to quickly copy this into what do we have? Graph, rep, exercises, everything here. So here's all the code. And you can actually see that we've got our Graph ADT here. And our graph array of edges implementation is here. So in this particular implementation, they have just like malloc 10,000, which is a terrible way to do it, right? Like the size of graph here. In fact, I don't even know if that's. Oh no, yeah, down here, g of n. I don't even know if that's used. What is that? Oh, g of n. Yeah, enough. Great. Yeah, so like here in theory, you'd probably be more likely to. Well, I guess it's hard because like at the start of this, you don't really know how many edges are there. Hamish says, "Why don't I just add Sublime to my path? Because I don't care." Lots of things. I see as you get older, I think it's a general thing. You start to realize like all these things you used to do you'd spend time trying to figure things out to save like a second here and there, and you're like, oh, I type in Sublime like 3 times a week for like 20 weeks a year. Anyway, so that's why I don't do it, because I'm jaded. So we have our graph rep. Vincent says, what does dynamically allocated mean? So when I say dynamically allocated, essentially there's 2 ways you can create an array with space. The first way is doing it at compile time with a stack array by saying something like edge E100. But if you don't know how big that array needs to be at compile time, which you actually do in this case here, then that's why you use malloc. So anything where the size of the array is going to either change throughout the program's running, or maybe change only once at the start, but you don't know how big it is. It's basically any time it depends on some kind of input that's not known at compile time. So in this case, for instance, like, you know, if a user was inputting, I think they're inputting V here, right? Well, they actually are. So see how they're inputting int V. I could just, the actual size of the array here, we should probably do is like V times V minus 1 all on 2. So this would probably be like a better way of doing it, because like 10,000 could be overkill for the size of the graph. So that's how much you'd actually malloc it by. That would be fine. But the thing is, you can't actually do this like a like compile time, because if I get rid of this enough for a second, I can't really say, oh, I'd like my edges array to actually be not like just a raw array like this. This would avoid any mallocs and stuff because it would be on the stack, but now it's like that doesn't work. That doesn't even make sense. Like, what's V in that context? And you can't like redefine it later. Like, you can't say graph edges is like 3 and then down here just be like, oh yeah, G edges is going to be a new edges thing of that. It's just not how the C language works. So anytime you don't know the size of something at compile time, you need to use malloc essentially, which is what we're doing here. Also, like, malloc is also useful if we want to resize that later. Like, if we wanted to start this off as just like V, and then when we insert things, just make it bigger later. So we have our new graph. Makes sense here. We're mallocing a graph rep. We're setting some variables. We're creating the edges array. So we're doing a malloc for the actual struct and a malloc for the edge array that the edges point to. And then a few other operations down here, like insert edge. This is that implementation of the pseudocode. It looks pretty much similar to the slides. Like, you can kind of look through this in your own time because it all works. Removing is the same kind of thing. Adjacency, a function that's been added here, where essentially if we want to check if two vertices are adjacent, then we loop through all of the edges. So we go from starting with I as 0, and then we loop through the number of edges that exist, and then we check if the edge, like, okay, so before that we actually created a new edge, and that edge data type's defined up in our .h file. So we create a new edge, we populate it with the two vertices passed in, and then we check if that edge is equal to the particular thing we're iterating through. You know, so you have your edge over here, and then you go through that array of edges and you compare them to every one. Now, one of the problems with this is that the edges might be the vertices might be the other way around. So that's why we actually have this equal function here, EQ, which you'll see defined up here. And what this does is this basically just checks both combinations. Because, like, you know, if 1's connected to 2 and you check is 2 connected to 1, that won't return true if you compare them directly, but you have to like swap them around to check. So this is just checking both permutations. That's what the equals function here is doing. You could do that inside this function here, but I think it's used a few other times in the code. Yeah, it's used like in most of these functions here. Because, you know, when you insert and when you remove, you need to check if things are there, basically. Yeah. Cool. So then you have show graph, which is just a simple for loop that goes through and prints everything. And then free graph that frees the edges array and then frees G itself. So, yeah. That's the array of edges implementation. I don't think there's a lot more to add there, except that in terms of the complexity of this implementation, the storage cost is typically the number of edges or worse. Best case, it's the number of edges if you're mallocing frequently. So it's like amortized roughly the number of edges, though it could be as big as V squared as we've done in this case here. Initializing it's very cheap because it's just a malloc. You don't have to repopulate anything. And inserting an edge and deleting an edge, because you have to loop through the entire array, that's also OE, where E is the number of edges. And as I said before, we can insert, we can reallocate the edges array when it's full. So we could start off smaller and make it bigger. And as I said also at the start, we could maintain order in the edges array, which will get the lookup time to O log E, which I haven't included the lookup time here, but the lookup time would be OE as well. So maintaining edges in order will allow for OE lookup, but again, you have to sort it, which is not trivial when it comes to an array. So are there any questions about the array of edges? What does amortized mean? So the idea of yeah, sure. So again, just to reiterate this concept. So if you were to have let's say you have an array, and to insert into it costs it's O1, right? Because you just add to the end. But the array is actually like a lot bigger. There's actually like 8 spots here for stuff. So when you insert the second element, it's also O1 because you just insert it to the end, and then it's also O1, and then it's also O1. So all the inserts are O1. But then randomly, once you get to the end here and you go to insert another thing, you have to do that full realloc where you actually like make a whole new like array twice as big, right? Like that. And then you have to copy everything across to that new array and delete it from the old array. And that operation of copying is time on. So then you ask yourself, okay, what's the actual time complexity of this, assuming that the array doubles every time? So it goes from like 8 to 16 to 32 to 64. And the term amortized analysis essentially is saying that sometimes when you're looking at analysis, every operation's O1, but occasionally you have some operations that are more complex. So they feel heavier. They feel more complicated to do. Like ON is like, oh, that's a complex operation to do because you got to loop through everything. However, if you look at the cost of this over a very big average, over like millions and billions of operations, the average kind of decreases. And the kind of intuitive examples that you're used to, again, I think I mentioned this back in week 1 or 2, was like, when you fly from like Sydney to Melbourne, or Sydney to Brisbane or something, it's like the cost of getting to the airport and checking in and waiting to hop on the plane feels like a lot. Like that setup cost feels like a lot. But when you fly overseas, for instance, on like a 20-hour flight, or say, a 15-hour flight to Texas in the US or something, the cost of getting to the airport and checking in and waiting gets, what you might say, like it gets like amortized out. It gets like averaged out by like the overall thing we're dealing with. It's essentially like these little operations that we have to do just kind of get made irrelevant as we think about the bigger picture. Sometimes, again, we refer to like amortization as a bit of a process of like doing a little bit of setup up front. So I think, again, back in week 2, I made the comments that if you have an array that's unsorted, like a long array that's unsorted, the lookup time is ON. But if you sort that array and then look it up, it's actually going to be, say, ON squared plus log n. The n squared is the sorting part, which we talk about in week 8, and the n squared is the sorting part, and the log n is the binary search part. So it's actually more expensive to sort it than search it. But if you know for a fact, yes, programming misplaced, that's correct. That's very funny. So if you know for a fact that you're going to only have to sort it once and then do no more inserts or removes, but then you can search it a million times after that, repeatedly, then the actual cost of this is like ON squared plus O log n plus O log n plus O log n. And it just kind of goes on like that. And then suddenly, after a million log n's, that n squared that you did at the start is like irrelevant. It's like, oh yeah, that was like a second. That, in the grand scheme of things, that took no time at all. So amortized analysis of things is kind of just saying, we ignore outliers. That's a bit of an oversimplification, because if the outliers happen regularly, then it's a bit of a problem. There was a forum post that I wrote, and there was some interesting confusion around it. I don't know if it's still there. I pinned it because it was interesting. That's the wrong course. This is course. Nope. I must have unpinned it. Oh, there we go. No, here it is. You should go check out this pin post because this was a really interesting question that I answered and then clarified later. But essentially, it's like this question was if you have to do an ON operation every 8 operations, it's still ON overall because it's like consistently throughout it. However, if it's like if the complex operation becomes less frequent, then as you kind of approach infinity, it becomes less like relevant, which is what's happening in realIC, because realIC does 8, then 16, then 32, then 64, and technically as you approach infinity, you don't even do it anymore. You know, so it literally becomes actually less relevant. Whereas something you do consistently but infrequently is it doesn't just disappear. Yeah, and James says in the chat, one could think of it as ignoring infrequent outliers. So if that's a good summary for people, like amortized analysis is essentially ignoring infrequent outliers, or outliers that become less frequent with time, might even be another way of saying it. That's what that is. Anyway, that was we spent 5 minutes on that because I think it's a really interesting topic, and I know I wasn't taught that very well when I did the course a long time ago. So there's the implementation for array of edges. Cool. Now okay, sorry, question snuck in. Waleed says, what about the case where the infrequent action happens, say, every billionth inputs? So that's a great question, because if you have something that does on, it's O1, it's constant time from 1 to operation 999 million, like, and then the billionth operation is On, but every billionth operation is that. Then technically speaking, the time complexity of this would be On. Because if you were to kind of look at it, it would be like O of 0.00000000001n or something like that. Like that would be its kind of raw complexity, right? Because over a billion operations, that's how much it would take. So in theory that would be On, but the reason that we kind of chatted about real time at the very start of our time complexity talk was because in reality no one would consider that kind of operation On. In a very theoretical sense, in a literal sense of big O notation, it would be On, but like no one would consider that On. I mean, nearly nothing is constant time in that sense, because even constant time operations might still need to, you know, do something super random, like every now and again. Like the computer will randomly need to stop a thread or just other BS. So yeah, good question though. So the second type of graph implementation that we're looking at is an adjacency matrix. Now, an adjacency matrix in a large sense will be the simplest type of structure for people to understand, because you store your graph as a giant table in Excel, essentially. So it's stored as a 2D array of edges. It's super easy to implement. It's relatively fast. It's just not very memory efficient. So if you have like a ton of RAM and you know the operation you're doing has a ton of RAM, then this is actually a great structure because it's quick. It's quick to operate with. It's very straightforward to implement, though again, just a lot of memory, which we'll talk about in a sec. So this undirected graph here that you see, if you were to store this as an adjacency matrix, it's a very straightforward structure. You have your nodes or your vertices on the left and the top, and then all of the space in between here is essentially like a 1 if there's an edge between it and a 0 if there's not. So you go, is there an edge between 0 and 0? No. Is there an edge between 0 and 1? Yes. Is there an edge between 0 and 2? No. And is there an edge between 0 and 3? Yes. That's the very straightforward structure of that. Yeah, so Kaya says it looks really neat. That's correct. It does feel neat, doesn't it? With undirected graphs, one thing you will notice about these adjacency matrices are that they are symmetrical about the diagonal this way. So you'll actually, and that makes sense because 1 and 0 is the same as 0 and 1, like that. So there's even more wasted space there, which we will talk about as well. But essentially you're creating an array for something like this. Now, the implementation of an adjacency matrix is pretty straightforward as well. You store the number of vertices in the graph. You store the number of edges. That's just a very useful thing to do. And then you have to store a 2D array of edges, and we're using ints here. That's not because the vertex is an int. In fact, this graph structure doesn't even store a notion of the vertex per se. It kind of treats the this is a very simplified graph, but in this case, it's like the vertices are kind of referring to indexes of vertices. Like these things up here, kind of, you would often just treat as like indexes. Again, very simplified graph structures where we're just dealing with numbers. So this is a 2D array. Okay, number of vertices, number of edges. Super simple. Mallocing a 2D array, not exactly the most simple thing to do in the world, but simple enough. It doesn't need to be a 2D array. You could make it a 1D array if you wanted to and be all fancy with your math and lookups. So, only people that... that's not fun. The pseudocode's pretty straightforward for this. When we create a new graph, we add the number of vertices in, we allocate the memory for the 2D array of edges. This part here is really important though. When you use an adjacency matrix, because when you when you grab memory in C, it's all uninitialized. So you have to initialize it. And that means that to actually initialize this entire adjacency matrix, you need 2 for loops here, right? Which is costly. Now, there's only 1 for loop in the pseudocode, but that's just because the pseudocode's pretty condensed. But yeah, so that's very costly. So that's one big penalty of an adjacency matrix, is that the setup is really expensive. When you insert an edge, super simple. You literally just look up the V and the W and then bam, add it in. Increase the number of edges in the graph. And then removing is the same thing. Look it up, set it to 0, decrease the number of edges in the graph. Show edges is like a tiny bit more complex than other graph structures, because you do have to loop through the entire 2D array to get everything. So it's also another like for loop and a for loop thing, which is definitely a bit slower than some other implementations. Now we can have a look at this structure in VLab as well, in graph adjacency matrix. So we see our graph representation up here. We have a new graph. I also just realized some of these names are slightly wrong. Again, so in the slides and stuff, I've, in the ADT, let me find it. So I've gone through and started trying to change some of these things to make more sense. And in the Graph ADT, you will see that I started changing the naming conventions here to graph new, graph edge insert and stuff. I still have to go and update that in the code on the CSE machines. So that's why you see that slight discrepancy. Again, I just think these are clearer and better convention than what's like here, new graph and things like this. So we have our insert, we have our remove. They're extremely straightforward. You know, when you say remove an edge is made up of a vertex left and a vertex right, and you simply set those edges and stuff to 0. Show graph, I have to do 2 for loops to actually loop through the entire thing. This doesn't look right. I didn't write this code originally, but this one doesn't look right to me. That if statement's in the wrong spot. Should be there. That'll make more sense. You have to do like a 2D loop through the whole thing, and then print out every edge if it exists. And then the freeing the graph's pretty simple, because again, you just have to free the yeah, that and this. Easy. Cool. Great. Graph adjacency matrix. Perfect. In terms of the complexity of the adjacency matrix, so as we said before, v squared here is the storage cost. It has a very high fixed storage cost because you even if you don't even if you have a few edges, you still end up allocating the entire 2D array. So it's really bad for sparse matrices. The initialization is v squared. So again, massive memory cost, massive setup cost, but the inserting and deleting of edges is quite quick. Lookup's very quick as well, O1, because you're just looking up a particular array index. And printing's a little bit slower because you do have to go through everything. So printing's also v squared. Like traversing is also v squared, which is kind of annoying. We mentioned before that the matrix is repeated about the diagonal axis. If you have an undirected graph, you can actually save some memory by only worrying about what's on like the top diagonal of that, like the top triangle. Though again, that's like added more complexity, and that's only a coefficient improvement. As in that just makes your graph effectively like half v squared or something. It doesn't actually change the big O notation. Kaya has asked a question, which is why doesn't it take 2 loops to free things? That's an excellent question. So the reason for that is that it doesn't actually take 2 loops to malloc things either. It's a little bit weird, but to malloc like one array requires like 1 malloc, and then to malloc a 2D array requires 1 malloc plus 1 like looped malloc. So it's a little bit strange because to do the first array you only need 1 malloc, and because if you think about, you got to think about a 2D array. I'll draw this up because that wasn't making any sense. A 2D array in a malloc sense, you malloc one array like this, which is the 1 dimension, and you only have to do 1 malloc for that, and then you just have to do 1 loop which goes and mallocs the actual like second part of the array here. So here's your first malloc, and then there's 1 for loop to go through all of those array items. So that's kind of why it looks like that. So what we're actually seeing here with the free is that this is removing all of like the rows, so to speak. It's going through each row and mallocing that array. And then the last malloc here, G edges, is actually deleting the whole column that all those rows sat in between. Okay, are there any other questions about adjacency matrices? See if anyone has any. Waleed says, so an adjacency matrix would be ideal when working with a connected graph. Yeah, I guess so. Yes, I mean the more edges the better. That's the short story. The other benefit of a... Sorry, I'm on the wrong slide. The other... Oh, what? Oh, that's just the wrong header. What? Oh. The other benefit of a adjacency matrix structure is that it's actually like somewhat more space efficient because you're representing the edges as just a number, like a true or false. And in fact, you could actually make this an array of chars or shorts or some like 1 or 2 byte structure. So for a full matrix, you're actually probably going to see some even greater storage improvements with a sparse matrix because like you're not kind of storing pairs of all the vertices. Because you could imagine if you think about like these structures here, like array of edges, you're storing like for every edge you have, you're not just storing like a bit, like a 1 or a 0, but you're storing like a whole like tuple with 2 vertices which themselves are ints. So every edge you store in a graph like this is going to be 8 bytes, assuming that your vertices are ints, like just numbers. Whereas in like a matrix implementation, you could make each edge only worth 1 byte. So in theory, you could see like a like a space improvement of like up to 8 times of actual. But again, that's 8. That's a coefficient saving. That's not like a time complexity change. That's just like, it might be an 8th v squared, or v squared on 8, which is still v squared anyway. Sweet. Okay, our last type of what in God's name did? Oh my God, I think I've actually. I think I must have got the wrong version of this up, because I remember this one and I fixed some things. I'm sorry. That's okay. It's just a tiny thing. This stupid freaking thing's wrong. So an adjacency list, you don't actually need that first slide, but an adjacency list is the last kind of array structure, and an adjacency list structure is kind of similar to an adjacency matrix in terms of the actual struct itself. You store the number of edges, the number of vertices, and some kind of pointer of pointers. It's not quite a 2D array, but it's like a pointer of pointers, except the way the structure actually works is that the first dimension here is an array, just like an adjacency matrix, because you're going to have an array for every vertex, but every item here doesn't point to another array. It actually points to a linked list. So it's actually an array of linked list structure, where if I have a graph like this, I have 4 nodes, so therefore my array has 4 spaces in it, and then each item is a linked list containing information about all of the ones it connects to. So if you look at this diagram for a second, you can pause the video, I guess, too, is like 0 here, the 0 vertex has an edge to 1 and an edge to 3. So the linked list has values 1 and 3 in it. The 1 has a edge to 0 and 3, so this has 0 and 3. 2 has an edge to just 3, and then 3 has an edge to 0, 1, and 2. So that actual edge information is stored this way. So we call it an adjacency list because we're keeping a series of lists of what nodes are adjacent to other nodes here. Like that. Any questions about that structure before we talk about the pseudocode or anything like that? Waleed says, so this is similar to what a sorted array of edges might look like if we sorted by the first edge in the tuple. I don't know. I don't really know if like that's how I'd refer to it. For me, it kind of feels like an adjacency matrix where each row we only store what's necessary. So instead of having like I kind of think of it like, instead of having a structure where you have like all the vertices and then each vertice has like all this information, like this, because it's arrays of arrays, it's actually like we only store what's necessary. So it's like arrays of lists, because we know lists are dynamically sized. So that's kind of how I think about it personally. Naturally, an adjacency list implementation will require a linked list implementation inside of it. So this is, we kind of have like a link. This is a linked list here, basically. Like this is a linked list structure. In terms of the pseudocode, when you create a new graph, you have to initialize the vertices and the edges. You have to allocate memory for the array of vertices, the column. But then for each one, you have to kind of create a new empty linked list. So when an adjacency list is initialized, you have to malloc the whole array up here, but then you also have to kind of, each item here points to null. Oh, it's raining, that's nice. So that's kind of how the data structure is initialized. When you insert an edge, when you're inserting an edge from V to W, you go down the array and you find the point where V is, and then you add W to this linked list. So then W might be here, so then this becomes like W pointing to null. So you're essentially like building out a structure like that. Removing is very similar. If you're removing the edge from V to W, you come down to V, then you have to traverse through its linked list and then remove the element from the linked list. So the half of this battle is actually just linked lists. So if you can get your head around linked lists, it's actually a very digestible data structure. And then showing the edges or printing the edges is quite straightforward. You simply loop through all of your vertices, you loop through all of their edges, and then you print them out. Now, the actual implementation I also have up here, the adjacency list. Very similar to the pseudocode. Or is this one? Yeah, very similar to the pseudocode, where, you know, we insert edges. We have a bunch of linked list functions here, which is actually all inside of list.c. So there's actually a lot more code to write in this one. So it's probably, like, I would say in general, adjacency lists, like if you could only pick one type of structure to store every graph in that you ever worked with, I feel personally like adjacency lists would probably be the most useful one on average. Definitely not in like all scenarios or anything like that, but it's relatively fast. It's relatively space efficient. It's just a bit more complex though. It's definitely the most complex to code, and you can kind of see this just by the fact that we have to have a linked list on top of this thing. In terms of the complexity of it, sorry about this title here, ignore that. The actual storage cost makes sense. It's the number of vertices plus the number of edges. So it's probably like, so because you always need to store the number of vertices, even if there's no edges in the graph. So for a graph with no edges, it's going to beat an adjacency matrix by a lot, but it's not going to beat an array of edges, because an array of edges would store nothing if the graph was empty. But it's got a pretty standard like delete, insertion, initialization. It's all kind of OV, and the reason for that is because when you actually look up the yeah, that is a typo. When you look, as I said, I actually fixed a lot of these, and I think I just put it in the wrong place, so I'll just fix that after the lecture. With array of edges, the way to think about it is that this is an array with an adjacency list. This is an array, and all the arrays are to linked lists. So the actual like lookup of the array is constant time, right? But then adding it to the linked list is, you know, adding it to the linked list is what takes the time. So finding the row to insert it into is instant, but then like all linked list insertions, it's like the length of the list. So someone says, wouldn't edge insert be OV? So all three of these are OV. The reason it's OV and not OE is because you just got to think about it. This is instant to look up. So the worst case we have is, what's the worst case complexity of inserting into this linked list? Well, any given vertice can only have V edges, right? Like if I have a graph with 5 nodes in it, V minus 1 edges. If I have a graph with 5 nodes in it, the most edges I can have as a vertex is 4. So therefore, the actual worst case of inserting into a linked list is 4. It's actually the number of vertices, not the number of edges. So, because this can only be size V. Each linked list can only be size V. Yeah, we both have to check that it's not a duplicate, and we have to insert through it. And Gorb says, why couldn't you just insert at the front of the list? It's pretty much for duplicate checking. Kai says, why is the lookup of V instant? It's the same reason that the lookup of an edge in an adjacency matrix is instant, because when we're dealing with array structures, in theory, the vertex gives us the index. Like in these kinds of graphs we've been looking at here, if we know, like you got to think about, it's a bit weird because it's a big oversimplification, but this graph here, these numbers represent indexes in a way. So it's like if I'm like, okay, this vertex is index 3, then I can just look up V3 in the array. And we know that array lookups are constant time. So that's why the array component's instant, and that's why lookups in adjacency matrices are instant too, because it's lookup row, lookup column, and that's all instant because of random access memory with arrays. Caleb says, can you make an edge that links a vertex to itself? Yes, that's probably my only thing I don't like about some of these slides that I've modified from previous terms, is that it lacks enough examples. I think there was one in the first lecture here. It is definitely possible to have a vertex that links to itself. That's totally normal. But back to the previous comments. So Kai said, I get the constant lookup thing, but that's only when we have positive integer nodes. Yes, in reality, you would probably be so in reality, what you might do, for instance, is keep a separate data structure, which is all of your vertices. So like you assign like a unique number or an index to each vertice, and you store those separately, and your graph is actually just a graph of indexes of those vertices, for instance. Or you could have a graph structure that actually stores those vertices themselves. So the best way to think about this is not that the graph stores numbers necessarily, but like the graph, well, this is not so much that the graph is operating on vertexes that are, the values are numbers, but rather the numbers here are representative of the vertexes. So they're kind of like indexes of the vertexes. That's why they're all like ordered from 0, 1, 2, 3. But it is a bit of an oversimplification, definitely. Yes, and then if we come back to this one, so this is kind of a summary of everything. There's definitely more operations than are listed here, that's for sure. But generally speaking, adjacency matrix is great for dense matrices, for dense graphs. That's, because it's so quick to do a lot of operations like insert and remove and checks. I haven't got like traverse in here, or I haven't got like check if it's in the graph, check if the edge is in the graph here. So expensive setup, but definitely worth it if your graph is quite dense. And array of edges are generally pretty quick. Though one thing you'll notice is that, in some cases, I don't think there's any... I think the only thing that's missing from... again, this table could be longer. We just picked some random things. Is like array of edges traversal is longer because you have to go through all the edges. So I think it's OE, whereas adjacency matrix lookup's OV. So array of edges is a generally pretty efficient thing except for lookup. And you'll kind of see this always where the faster something is to look up, generally the longer it takes to modify, and then generally the more memory it uses. And it's quite an extreme example here where an adjacency matrix is really quick to look up, super expensive to set up, and very memory intensive. An adjacency list somewhere in the middle, it's like pretty quick to insert, pretty quick to remove, pretty quick to set up, pretty quick to like search. And an array of edges is kind of like pretty slow to look up, but pretty quick to do other things as well. So that's kind of the summary of that. And yeah, 352. Any last questions? I'll leave the slide up while we go through any last questions. But they're essentially the three core graph implementations. As I said, I know there's a couple of typos we saw in those slides. I'll fix those up this afternoon, probably tonight, just so no one's confused about anything. Thanks again for being patient. Again, these are new lecture slides, so sometimes things happen. Waleed says, anywhere we can find the explanation of OE times log V for is path. Probably not at the moment. I think that, this is just included there for completeness, but I think traversal is the only thing really missing. That'll probably make more sense because later this week, and in particular in week 7, we're going to do more about traversals and path findings and things like that. So I probably wouldn't spend much time worrying about that at the moment. Exactly. Most of this graph stuff is this is in a lot of ways this is the beginning of the content you need for assignment 2, which isn't out for quite a while. So yeah. Any other last pressing questions? Otherwise, we'll leave them for the forum. Will assignment be due week 10? Yes, will. Yep, due in week 10. You're not allowed to have anything due in week 11 anymore. At least not in the engineering faculty. At least not if you play by the rules. Okay, well, thanks everyone. I hope you have a great afternoon or evening, and for those watching later, I hope you have a good whatever you're doing. And don't forget to leave some feedback. As always, thank you for that.